This narrated PowerPoint does derivations for means and variances of averages. In many ways, the material in section 5 of this week's reader parallels the material in section 4, where we worked with means and variances of sums. Going forward in our course, the results for means and variances of averages are going to be even more important than means and variances of sums. So what we're looking at is a conceptual framework where we're thinking about the mean of x bar from all possible samples. This is a highly theoretical background for practical problems because in most practical applications we're only going to have the average x bar from a single sample, but we need to think about all possible samples to get the theoretical results we need for our practical work. So the key insight in this section is that the sample average x bar is a linear transformation of the sum I equal 1 to n of x sub I. That's another reason we started this week's materials looking at linear transformations of random variables. The formula for the sample average x bar is simply 1 over n times the sum of the x sub I. So we're looking at a transformation of the sum with a known multiplicative constant, 1 over n. So in theoretical derivations, the expected value of x bar from all possible samples is the expected value of 1 over n times the sum. That constant 1 over n comes out in front of the expectation, 1 over n times the expected value of the sum. And then we know from our work in section 4 that this is simply equal to that constant 1 over n again times the sum of the expected values of the random variables x sub I. And for homogeneous populations, the random variables x sub I all have the same distribution and the same expected value. So what we've got here algebraically is the expected value of the sample average x bar is 1 over n times n times the expected value of x. And of course that 1 over n and n will cancel, and the expected value of x bar is just e of x, or to use the alternative notation for the population mean, mu. So what we've shown here is that the mean of the x bars from all possible samples is the population mean mu. Now we need to be careful here, because if we take a lot of samples of size n from the same population, the sample averages x bar can vary quite a bit. But we're going to think of these x bars from all possible samples as a population. And what we're saying in the work from the previous slide is that over all possible samples, the x bar values average out to be the population mean mu. So in symbols, e of x bar is equal to mu. Baldi and Moore have a nice discussion of this on pages 318 and 319. Again, each sample average x bar is an estimate of the population mean mu. And when the population of the statistic values from all possible samples average out to the right value, in quotes, the population value of the parameter, we say that the statistic we're using is an unbiased estimator. So what we've shown is that the sample average x bar is an unbiased estimator of the population mean mu. And we need to be careful, because unbiased is a technical term here. It's not a value judgment. And the term bias is one that is also used in epidemiology, although in a slightly different way. Also, looking ahead, some widely used statistical estimators, such as a relative risk or an odds ratio for a sample, are not unbiased, but they're still really good and important estimators. The other caution is don't be overly impressed that in the long run the sample averages x bar average out to the population mean mu. X bar from a single sample can still be pretty far from mu, and so that's why next we have to look at the spread or the dispersion of these sample average values. So we're going to want a standard deviation of x bar from all possible samples. And again, I want to keep saying this. If we take a lot of samples of the same size from the same population, we're going to get, in principle, a different average x bar from every sample, and these can vary quite a bit. So we're again thinking of these x bar values as the population. We take all these samples and we just take the one summary number and throw away the observations. And so these x bar values are going to have a standard deviation, which of course is another key feature of the sampling distribution. And before we take a look at the formulas, I want to give you a little framework and say that the standard deviation of the x bar values is a function of two things. First of all, it's a function of the standard deviation sigma of the x values, and it's also a function of the sample size n. So here we go for the algebra. And in order to get the standard deviation of x bar, we're going to use exactly the same insight we did for finding the mean of the x bar values, and that is, of course, that the sample average x bar is a linear transformation of the sum of the xi, right? There's the formula. X bar is 1 over n times the sum of the x sub I. So the variance of x bar is the variance of 1 over n times the sum of the xi. And the way the linear transformations work on the variance scale, when we bring the constant outside, we have 1 over n squared times the variance of the x sub I. And here we need to be really careful when we're working with the sample. The random variables x sub I are independent, so we can actually write this as 1 over n squared times the sum of the variance of the x sub I. And we couldn't make this simplification if we didn't know the xi were independent from our random sampling. Finally, again for the special case of homogeneous populations, the random variables x sub I all have the same distribution and the same variance. So this formula further simplifies to the variance of x bar is equal to 1 over n squared times n times the variance of x. Again, we have some cancellation. What we're going to have, if we use the notation sigma squared for the variance of x, the variance of x bar is sigma squared over n. So to go back to the square root scale, we'll take the standard deviation of x bar is going to be sigma over root n. And a couple of comments about the implication in this formula. The larger the sample size, the smaller the standard deviation of the x bar values. The larger the sample size, the more concentrated will that sampling distribution be around the mean mu. Now, we've been interpreting standard deviation in week 1 as a typical distance of an observation from its average. So in this context, the standard deviation of x bar tells us how far off a typical sample average is from the population mean mu. Finally, here's an illustration from the reader where we can look at the spread of x bar values for samples of size 100 and samples of size 400 from the same population. This is looking at 10,000 samples to give us a pretty good picture of what the distribution of the sample averages would look like. I had Stata keep the same vertical axis scale so that you could see both of these distributions of x bar are centered around the population mean mu of 66 inches, but for samples of size 400, the x bars are much more concentrated around 66. So this is a preview of the mean and the spread of x bar values. Later on, we're going to also be looking at the shapes of these distributions, and in particular, especially the top one in this slide looks pretty much like a symmetric bell curve. So we're going to get to that pretty soon after we talk about means and variances and standard deviations for counts and proportions.